Okay, so hello everybody. I'm Ladislau Boloni. I'm a professor in computer science. I had already did a presentation like maybe 2 years ago, I guess. So I'm the kind of stuff which I'm doing these days is more or less the same kind of stuff which I was doing 2 years ago. So I'm primarily an artificial intelligence, machine learning, these days deep learning researcher who's also interested in particular applications, in particular in robotics and then other things like social behavior modeling and networking and other stuff like that. And in general, I'm trying to apply the tools of artificial intelligence towards improving results in other fields. And so I was thinking that, okay, well, here you are 2 years later. What's the current things which are going on in the artificial intelligence community, and maybe thinking about how my research applies to that. And one thing which may be totally obvious for somebody who is in artificial intelligence, but maybe it's not quite as obvious if somebody is outside on that, is that in the last 5 years, ever since a famous paper called Attention is All You Need, the trends in artificial intelligence were towards these very large models. And the idea is that they are based on a neural network subcomponent called transformer. And the idea is that you are building a very huge model, which is essentially trained on huge amount of data. And I think typically the whole internet, like everything you can scrape from the internet, is going to be filled in these models. And you end up creating these huge models. And GPT-3 is a very famous model on this one. They are usually called language models. But there are these days, they are also combinations of language models with visual models and sometimes with action models. So you just build a very, very large model, and then this pre-trained model. And now, so these are amazing. So if you look at YouTube and you look at new results in AI, you are going to see all these beautiful pictures generated by artificial intelligence. All these are like kind of coming out of this. Now, from a theoretical point of view, these models, there are a couple of things which are very interesting about them. One of them, it says that what matters is the huge quantity of data and the brute force computation. The cost of training these models is staggering. And we are talking about millions of dollars in computing cost. For instance, paid on Amazon AWS or something like this in order to train something like this. So if you have something like a system with, you have 10,000 graphics cards and you use them for half a year, or something like this. The architecture matters very little. In the last 5 years, all these components, everything seems to be transformers, and what people realized is that, at least at the stage in which we are, is that the architecture matters comparatively little. What matters is the amount of data you put in and the amount of money you pay in terms of computation. So this is an interesting result, which is kind of counterintuitive. And there are, I want to point out two statements from very famous people. One of them is from Geoff Hinton, who can be considered as the father or grandfather of the current deep learning models. And one statement which he is saying is that neural networks are going to go all the way. It says that deep neural networks trained with stochastic gradient descent are going to take us all the way to human equivalent intelligence, which kind of means that we are going to go to the singularity with no other architectural network. It's going to be all neural networks up to there. So that's a challenging, that's an interesting thing to my mind. coming from somebody who is accepted as being the father of these models. And the other one is from Rich Sutton, who is, again, kind of accepted as being the father of reinforcement learning, who says that he learned a bitter lesson. And the bitter lesson was that in the last 70 years of AI research is that general methods that average computation are ultimately the more effective, and by a large margin, meaning that humans are trying to be clever. We are trying to introduce human intelligence, human knowledge in our models. And then somebody comes with the general model, but get more computation, and it's just going to trump it. So all these things appear to be a very bad outcome for university research, because the point here is that we just do not have the money to train models like this. All these very large models had been trained by companies or by government-funded entities, let's say in China or Russia or places like this. We were never going to have, like my lab, we're never going to have the compute power to compete with Google, with Microsoft, or with Meta. Also, companies are going to have more data than us. They cannot share this with us. So the question is, what kind of stuff which we can do? And I want to point out that that people seem to misunderstand this situation, because what I personally think, and I think people misunderstand the Geoff Hinton and Rich Sutton statements as well, is that research on finding better, faster, more data efficient algorithms which go faster, which don't need that much data, the one algorithms which don't need that much compute power are going to be much more are going to be the ones which are going to drive us towards the future. And I wanted to point here. So I thought I'm gonna show a couple of papers which had been done by recently graduated students of mine, which are kind of going in this direction. So the general direction here is that we are trying to be clever in the sense of being more efficient, lowering the amount of information we need, lowering the amount of data we need, lowering the amount of computation we need. So here is one example, which is from an ICLR 2021 paper, which is on the topic of meta-learning. So meta-learning allows few-shot learning. So instead of requiring tens of millions of data points in order to learn a classifier, let's say for a visual classifier, meta-learning allows you to do learning based on a small number of examples. For example, one example of 5 examples of each. And this creates, and of course, this one is a great thing. And techniques such as MAML, introduced by Chelsea Finn and others from Berkeley, had demonstrated significant results on this. But the problem with this one is that you have a second phase, the preliminary phase, the meta-learning phase, and then on the meta-learning phase is the one where you need a lot of data. So our previous work, we have called UNCTRA, we made a further step in which we allow to do meta-learning without any kind of labels. So you can imagine that it's much easier to get data if you don't have to manually label them what is the content. You just get a bunch of data, randomly download it from the internet, and it's labeled, not labeled, you can train on that. So now the next step, which was this paper, was what can we do if we don't have any kind of data? Maybe we just have some kind of a generator algorithm, like a generative adversarial network or a variational autoencoder, and we just take out the generator part of the variational autoencoder. And so what we did is that we implemented an algorithm which we called latent space interpolation in unsupervised meta learning, LASIM. And so the idea with this one is that you can see all these pictures in different variations. These are the training data which we used for our algorithms. And now the fun part of this training data is that none of these training data really exists. All this training data had been just generated automatically. So the general idea is that if we have a certain latent space, which has certain properties, then we can say that if you have two pieces which are close, 2 points, two multidimensional points which are close to each other, let's say these two which I'm pointing out here, which are close to each other, these are going to generate images, in this case faces, which you can say that they are in the same class. And then if you have points which are, on the other hand, far away from each other, like say these two, then you can say that these are very likely going to be different people. And so we generate our own data. So the interesting part here is that there is no data whatsoever existing for this training. Now, of course, at some point, somebody had to train a generator, but no data is really used. So what performance do you achieve with something like this? And so you can look at performance data here, and these ones with the LASIM obtain classification performance. And you can see that at least at the moment in which this paper had been published, these techniques achieved the highest classification performance from all the models which had been which are unsupervised learning based. Now, of course, if you compare them with the algorithms which had been used supervised data, they are kind of weaker, right? So we are like somewhere at 95% instead of 98%. But the interesting part on this is that these algorithms had used only 25 labeled training data instead of 25,000. So it's an interesting technique which allows you to do a lot more with much less data. And I think I'm going to stop here.